Example problem 6 asks us to calculate the de Broglie wavelength of an electron traveling at 100 kilometers per hour. And then it tells us that 1 hour equals 3,600 seconds. So the two equations we're going to be using are going to be this equation and this equation. And you'll often have to jump back and forth between the two to figure out exactly what the de Broglie wavelength of a particular electron being or energy being is. So we're told that the electron is traveling, and so when something is traveling, we know that that's typically a velocity. So we know that something is traveling at 100 kilometers per hour. But we know if we go back over to the previous slide that v, our velocities, need to be measured in units of meters per second. So to meters per second. So this becomes another one of those compound problems where you have to convert the top and the bottom. So first we're going to handle the top, kilometers to meters, and that would handle the meter part. And you could do this in two separate steps if you wanted to. I'm just going to go ahead and do it in one step. So hours would go to the top and seconds could go to the bottom. If you forgot that 1 hour is 3,600 seconds, you absolutely could go from hours to minutes and then minutes to seconds if you wanted to, but we're going to cut that out of this problem. And so that would be your meters per second conversion here. So we give the 1 to the thing with the prefix and the metric system constant to the base unit, which is 1 times 10 to the third for kilo. And then the conversion from hours to seconds is a direct conversion. In 1 hour, there are 3,600 seconds. So putting this into our calculator, 100 times 1e to the third divided by 3,600 gives us 27.77 meters per second, and that's going to be our V. So if we look at the de Broglie wavelength formula, it looks like this. So wavelength equals h, which is Planck's constant, divided by p, which is going to be particle momentum. There's not a velocity anywhere in that equation. And so that's what I meant by us having to bounce back and forth between this equation and this equation, because the bottom equation has the velocity in it. So particle momentum equals the mass of an electron times that velocity. And so we've calculated V here. The mass of an electron is going to be one of those constants, and it's going to be the same every single time. So the mass of an electron all the time on the constant equation sheet is going to be 9.11 times 10 to the minus 31 kilograms. And so now we're ready to calculate P. So P equals 9.11 times 10 to the minus 31 kilograms times this V that we calculated. So 27.77 meters per second. And I'm going to go ahead and put my calculator in scientific mode because times 10 to the minus 31 is a very, very small number. Lots and lots of zeros. So open parentheses, 9.11 second E minus 31, close parentheses, open parentheses, 27.77, close parentheses, equals a particle momentum of 2.529, so 2.529 times 10 to the minus 29. And if we go back to the first page, you can see that particle momentum is measured in kilogram meters per second. So kilogram meters per second. And that makes sense because you see here, you're just multiplying kilograms by meters per second. It doesn't go anywhere. Nothing can cancel. So now we have our p-value. We're trying to calculate this wavelength here. H is going to be another one of those constants. H is called Planck's constant, and it's always going to be 6.626 times 10 to the minus 34 joules per second. And joules is one of those measurements of energy. And then we have our value for P, which we calculated in the previous equation. So putting that into the de Broglie wavelength equation, wavelength equals 6.626 times 10 to the minus 34 joules per second, divided by the P that we calculated. So 2.529 times 10 to the minus 29 kilogram meters per second. Put that into your calculator. So 6.626 second e to the minus 34, close parentheses, divided by open parentheses, 2.529 second e to the minus 29, close parentheses. That is going to give you a wavelength of 2.62 times 10 to the minus 5 meters. Let me know if you have any questions about how to work example problem 6.